Hello, welcome to the first edition of Valve Studio. It's March 9th, 2016. This is going to be a long edition. There's a lot of things to cover, but let's get started. So I got interested in looking into vacuum tubes with this radio that I purchased a long time ago. This is a 1932 Philco 91B, and I wanted to actually get it running again. So I learned a little bit about vacuum tubes and went in and actually fixed this guy. All he really needed was some filter capacitors, and he started up. And that kind of led me into this crazy thing that's been going on in my life for the last couple of years, and that is learning about vacuum tubes. I never learned about them in college. I'm a little too young for that. By the time I got to school, everything was BJTs and then eventually CMOS. So I didn't learn anything about vacuum tubes other than we used to go down to Anderson's Pharmacy and put our tubes in the tube tester to see if they were good or not. So for the past 2 years, it's been my my private research topic is vacuum tubes, and I'm going to talk a little bit about some things that have happened to bring you up to speed. One thing I'm going to go over is a class that I'm going to teach actually with Dr. Allen at Georgia Tech. And I'm going to do the experiment. So I'm getting geared up for that, and we'll talk a little bit about that in a few minutes. So this is the first thing that I actually renovated. But I didn't do this first. I worked on a few things before that. I found this in the free box at a garage sale. This is an old mono amplifier. This is a Olson, I don't know, it's probably 12 watt amplifier. And it is a push-pull EL84 design. And I took this all apart and got it running again. This is one of my pictures of the day from June of 2014. I didn't really know much about things going on back then, but this is what really fueled my passion to looking into this and figuring out how these tube amplifiers worked. So I have a lot of equipment now to actually do tube amplifier debugging and testing, and I'm learning more about the theory of it, and that's what we're going to talk about today. My first steps towards that. So the next thing I ended up doing after this was I found this site. It's called tubebooks.org, and these are there's probably 100 books over here in PDF form, and I started looking through these books. But where do you possibly start? This was an entire technology up until about 1975 or so. Where do you get started? I mean, I'm an analog circuit designer, but I've never done any of this, so I had a lot of difficulties trying to figure out where the information is that I wanted. Coming from a transistor background, how do I go back in time and learn about vacuum tubes? Well, I did a lot of reading on forums and what people, what the approaches they use, and I watched a lot of YouTube videos, and most of the content that I was able to find online on the video forum was like people repairing guitar amplifiers or doing a vintage radio repair. There wasn't much of a lot of theory in how to do transistor design. It was more like here's some tried and true methods. This is a rule of thumb. I don't really understand why this works this way, but people have done this before. It's things like that, and it wasn't the material that I was looking for, but I kept looking. I ended up buying some textbooks at a estate sale in Los Alamos. These are tube textbooks at the college level, and these particular books are written, they were written back in the 50s. And the techniques that they use for numerical analysis and that kind of thing, well, it's kind of dated. It's, I don't want to learn how to use a slide rule to understand how to do design with the philosophies that they teach in these books here. So I kept looking, okay? And along the way, there's some key books that I actually ended up purchasing. You can see back here, I have this book here. This is the RCA Receiving Tube Manual, RC22. I got this for my birthday. Josh bought this for me on eBay. This is an invaluable resource. This has probably got 600 data sheets in it, or abbreviations of data sheets. A along the way. This is from the year I was born, 1963. So that book is 53 years old. This book has got a lot of information in it, but again, it's not at the design level per se. It's more like how to repair things at a technician level. But still, this is one of the books I always have out, and it's handy that it's read. I can easily find it. The next book I bought was, I got this off eBay, this Radiotron Designer's Handbook. I got my version. I found it, some lady had it at a book sale in Livermore. So I now have this book. Now this book is giant. And it has approximately, I would say about 800 pages of notes out of the 1,400 concerning audio amplifiers. So I started going through that. That book is very, it's very intense reading. It's really designed for someone who wants to use it as a reference, not as a, here's how you get started. That'll be kind of invaluable after I figure out what's going on. I can actually go in and refer to that, but that's not the book I was looking for. Which leads me to the way that I eventually stumbled on this thing called Child's Law. These are the semiconductor physics research that this guy named Childs did in 1911. And he was joined by somebody named Langmuir. And those two guys together created this thing called the three-halves power law. You can see it here. This is talking about current density based on the electron flow through a vacuum tube. So this is the key component, the research down at the semiconductor physics level. And I found a paper that kind of summarizes this up called Thermionic Emission. And this goes into all the physics of the way the electrons flow. This is a little bit too, this is too in-depth. I don't really need to go all the way down to how the electrons flow in a vacuum tube, but you can see it's rather intense at some, the equations get unreally. And all I really want to know is how to make a guitar amplifier. So I'm not going to go into this at this level. However, like here's some triple integrals. So it's not, but all the theory that was derived more than 100 years ago is what drives these vacuum tubes. So if you don't want to learn that, how do you get started? I went over thermionic emission. So in my life, circuit simulations played a major role. So I started looking around at the vacuum tube models for SPICE. And the first one that I stumbled on actually was by Marshall Leach. He's a professor at Georgia Tech, and he was actually there. Well, I was there when he was a professor, and I took a class from Dr. Leach. And 2 years after I graduated, he published this paper, SPICE Models for Vacuum Tube Amplifiers. And if you look at this, that paper is very close to it came kind of the same conclusion that number 2 here came up with from Scott Reynolds. So those guys were looking at vacuum tubes back in the 90s. Here's a picture of Dr. Leach right here. He was on the same floor as I was at Georgia Tech in the Van Leer building. So his model comes up. This is a model this is a simulation output for a pentode, for a 6L6 beam triode, a pentode beam power tube. This is his simulation results. So here's the anode current, here's the screen current. And a real, this is somewhat close to a tube, vacuum tube, but here's the curve from a real vacuum tube. This is from the RCA manual that I just showed you for a 6L6. You can see the similarities here. The critics of the Leach model is the fact that in this region here, this knee is too sharp, okay? And you can see that this kind of has a gradual slope down and then it falls off. So this knee is too sharp. So people have been critical of this model. Now, because when you make a output transformer with a 6L6 tube, there's a chance that you'll be operating over a swing of voltage like this. And what this sloping down does is affect your your harmonic distortion. So people have taken Leach's model, this Leach and the Reynolds model, and actually applied transformations to it to make it more accurate. And that's what we're going to talk about today. So this guy here, Norman Corin, he got started looking at things. He was passionate about this for quite some time, and he has a model, circuit simulation model, that he came up with that modifies Leach's work. He did this for about 9 years, and then he eventually got that bug out of his system. Now he's a photographer over in Boulder. Then I ran into this guy here. This guy's name is Menno van der Veen. He's in the Netherlands, and he has continued to work on this. And his research interest for the last 30 years has been the interaction of the vacuum output tubes with the output transformer, which is another critical component. So I ended up reading some of the papers that he wrote for the Audio Engineering Society. And I wrote him because I wanted to find some more of these that weren't available, and he copied them or scanned them and sent them to me, and they were really quite fascinating, so I bought his book. This is his book here. It's called High-End Valve Amplifiers. He's got about 6 books now, and I have that one as well right here. This book, chapter 1, took me in that book about 3 weeks to get through, and I haven't got onto the transformers yet. I was just looking at his models for vacuum tubes themselves. So what I'm just going to call him Menno. What Menno does is here's the RCA manual that I showed you before for the. Let's just talk about the 12AX7, which is a high mu twin triode. This is what's used as the primary preamp tube in like a lot of amplifiers. Probably 99.97% of all guitar amplifiers have one of these as the preamp. So unfortunately, this RCA manual only has the bias points here for running in a Class A. There's not really any curves in here, but you can, however, go download data sheets. Where is this data sheet? Here it is. Data sheets from, this is the RCA data sheet for the 12AX7. And so what's in the receiving manual is just a summary of this page here. So if we scroll down here, we get to this point where we have these curves. Okay, so there's the curve here. Let me go ahead and rotate this thing. Did I go the right way? Nope. Okay, so these are the anode or plate milliamp curves versus the gate voltage and the anode voltage itself on the x-axis. So what Menno does is he actually, in his model, he's able to take these. Where is that data? Oh, there's no data here at all. Let me go up and look at a tube up above here. This one's a little bit more, has more information. Okay, so here's the characteristics for a 12AU7. What Menno does is he takes these values here and he back calculates out to get the SPICE model parameters for this triode tube. Now let me see if I can find what I'm looking for here. I got it somewhere in here. Where did I put that dang thing? Okay. Here's the triode model that kind of most people use. This is that three halves model that came out of the Child-Langmuir equations. It basically says that the anode current is equal to some K value times the gate cathode voltage plus some dA parameter times the voltage on the anode to cathode to the 3/2 power. So what Menno does is you need to calculate somehow K and dA for a tube you want to interested in using in a simulation package. So what Menno did in his book was he took this data here, these characteristic data, these 6 values or so, and he's able to determine what K and dA are. So from that, he's able to produce some curves, and he matched up pretty well. Which leads me to what I was doing was, if you only pick one bias point and calculate K and dA, it's really mostly accurate around that that bias point. But if you look at the manual here, they give you 2 bias points, one at a plate voltage of 100 volts and the other one at 250. If you're going to run somewhere else, or you got different grid voltages, you're going to run somewhere else, it's fairly difficult to know if you're going to be accurate if you create your SPICE parameters at a particular bias point. You can use the graph, though. You can use this graph from here to actually use it as a design tool, and that's what most designs, the approach to doing this kind of design does, is you come up with this graph, you plot this thing called a load line, and you put your operating point on the load line, and then you're going to vary around that load line based on your fixed, you're going to operate around that operating point based on your fixed load line. Okay, well, now we're going to get kind of complicated here. Let me switch over to this. So I spent quite some time, let me see, where was I? That's his book. I did that one. So what I really wanted to look at was, let's take Menno's approach and actually do some optimization and use some nonlinear solvers to determine what K and D are. So I started looking at SciPy. This is a scientific library for Python, and particularly I found this thing called SciPy Optimized Curve Fit. So what this does is it allows you to take a bunch of experimental data and the theoretical equations you're interested in matching to that experimental data to determine the parameters that you don't actually know. So I took the examples out of Menno's chapter 1 book and ran them through an optimization curve fit from SciPy. And this is actually this is the approach that he did in his book. So he measured these things right here. These are 2 operating points that he had. And then in his book, what he does is he does an iterative approach to finding out what K and dA are. Now this book was written in 1999, so I kind of updated that today. I ran this through SciPy's optimized routine. So I wrote a couple functions here, and then I called this thing called fsolve. And what fsolve did was it came out and it calculated K and dA. And these ones actually match with the example in his book, so that's good. But that still looks at two points over the curve. And if you look at these values here, he's kind of going from cathode voltage of, or a anode voltage of 197 volts down to 316. So if he's on this curve here, he's going from about here to about here, which is a fair place to be operating for one of these triodes. All right, so I wanted to do something a little bit more accurate than that. So what I did was I took this data out of this. I extracted this data using a thing called Engage. I don't have that link up here. I use this thing. This is called a, you can open up graphs that are images, and this will help you extract the data that created the original image. So I downloaded this and got this running on my computer, and then I looked at using Python's optimize module. So I took the real data from the data sheet that I extracted the points from, and I ran it through SciPy's optimized curve fit algorithm right here. Okay, and I got fairly good results from this. So my value of D and A that you need for the SPICE model is optimized against the actual triode curves that came out of a curve tracer. Are you following me? All right, so now I have K and DA. Now let's go screaming forward to about 2 months ago. So I'm talking to Dr. Allen, and I told him, I said, hey, I haven't talked to him in about 10 years. I said, I've been looking at these tube stuff, and I'm having some problems kind of figuring out how things are worked together, and doing things at a collegiate level design class. They just don't have the information handy, and it's not in a form that I can actually consume. So he suggested that we teach a class together. So he would do the lecture and I would do the experiment, which is great because content like this doesn't really quite exist. We're going to offer it on a online university. It'll be about maybe 15 lectures and probably about 30 different labs or experiments. I'm very excited about this. I stay up late at night till 3 in the morning playing around with these equations and reading about tubes and vacuum tubes and amplifiers and all this kind of stuff. That's why I'm doing this now. So my approach is to write a Python program to do this optimization using SciPy's optimize routine. That might be too much to ask for someone who just wants to learn how a guitar amplifier works, because they'd have to get Python running. Then they'd have to download the libraries, and they'd have to do all that kind of stuff. And I also need a way to document it. So I can't just slap out a piece of Python code. So I started looking at how to do the documentation and the Python code together so that someone could actually run something very simplistic. I mean, not much setup to get their development environment to do this numerical analysis on their desktop running. So I looked at this thing called iPython notebooks. It's called Jupyter, but an iPython notebook is it's a thing that runs in your browser, and it lets you run Python code in your browser, and also the accompanied documentation goes along with the Python code. And this iPython notebook's been around for quite some time. I didn't look at it very much until about 3 days ago. And this is ideal for what I want to do. So what I can do is create one of these notebooks with my simulation code. And then someone who's taken the class, one of my students, can download my notebook file and actually run my examples on their computer themselves. In order to do that, though, they need to install Python and make that simple. So this thing called Anaconda is a Python distribution. You can download Python in a lot of different ways, but Anaconda includes a lot of popular Python packages. So in one location with one install, you can download Anaconda and get it going, and then you can have almost all your stuff there. And you don't have to worry about if you're on Windows or Macintosh or Linux or whatever it is. You can download Anaconda and get it going. It's very simple. And there's a couple of programs there, and then you can do everything just straight out of Anaconda. Anaconda supports the notebooks. So what I have here is I'm running Jupyter. I downloaded Anaconda on my Linux desktop. So Jupyter's running now, and we're going to go in and look at my model equations here. I think that's over here. So here's my Wait, I'm getting a little bit confused here. I'm in the wrong tab. Okay, so this is what it looks like. A Python notebook. So I have some documentation here. Here's the equation I'm trying to solve, and I'm looking for K and D. So here's some Python code right here, and so I'm going to go ahead and run that here. Here's the data sheet that I got. I'm using an ECC 83. This is what to use in this book. ECC 83 is the British version of the 12AX7. So here's those characteristic curves. And then this is what the output looked like. Let me close some of this stuff up here. So here's the data points that I actually extracted using that program called Engage. And I created a data table. And I go down and explain how to create this data table. And then ultimately this thing creates a CSV file of those different curves. And then I go massage that data so that it's in the kind of the right format. All right, now down to my routine. Now this is the same Python code that I wrote with just a straight Python file itself. I just pasted it right in here and I got this to run. So this is the curve fit routine here, where this is curve fitting K and DA. Okay. Now down below, so here's what my value of K and DA ended up being. And then I got to calculate a bunch of curves because I want to overlay the original data from the extracted data sheet with the model that I'm using and look at the two things at the same time. So if you get down to the bottom, the very end of this thing, I don't know what that was about, but let's just go down here. Okay, here's the this is the model data. All right, the dots are the data that is extracted from the data sheet, and using K and DA that I calculate, these are the curves that I would get out if I used that model from up at the top. If I use this model right here in my circuit simulation, I would get these bottom curves here. Okay, so you can see that we're kind of close. We're close enough. This could use further optimization, which I'm going to look at soon. But we're looking pretty good. So what this tells me is that what I can do is take a data sheet, the curves from a data sheet, and optimize the parameters to create the circuit simulation model. And then from there, I can use SPICE to do my circuit simulation. This is all great. Now let's go on to the next step. In order for my students to run my notebook file, they had to download Anaconda, and then they had to download my notebook file. Now I have my notebook file on my GitHub page right here. This is under my, I've created a project at my GitHub page for Holo 2040. It's called Valve Studio, and I put all my models in here. So if you want to download one of these models and play with it, here's the notebook file right here that I'm actually running, and it runs. I mean, if you go back over here and you change any of these parameters, you can rerun this Python code right here and look at the results right below. This all runs in the browser. Now Python's running in the background on my desktop machine, but the browser is the main interface to look at both documentation, Python code, and the Python results. It's really quite clever on how this works. So one of my students would have to come over to my GitHub page, download this. This is called a iPython notebook file. Download that, download Anaconda, and then I'll get everything running just to change values and play with my examples. So I was thinking, there's got to be a way. Somebody has to be hosting this part, and sure enough, they are. And I found this thing here. It's called MyBinder, So this way, MyBinder is a Docker-driven hosted environment that creates a Docker image to run iPython notebooks. And I can point my GitHub repo at that and create a virtual machine to run my notebook. So let's go ahead and do that. So what we need here is we need this URL right here. This is the Git URL, and I'm going to come down here, and it says tell us what your GitHub repo is. So I'm going to paste that in, and down here under dependencies, I don't need any dependencies. I don't need any attached services. All right. So what this is doing, it's going up and it's building a Docker image right now of all the files that I need to have in order to run my Valve Studio. So this eliminates the Anaconda download section. You don't have to do anything. The students themselves can run all my examples without downloading anything or configuring anything. And this is really cool. This is the way with this thing at MyBinder is going to allow people to actually run iPython notebooks wherever they are without having to do anything. They can just run everything in their browser, and the back end hosts all the simulation part of it. So this thing is building up a bunch of stuff here. It's going to take just a few minutes. Probably running during the day here is probably bad news. I was doing this about 3 in the morning. It was actually pretty quick. But it doesn't take much time to do that. I'll go ahead and be quiet. I'll just zoom forward until we get to it working. Okay, so it looks like it's very close to being done here. Successfully built everything here. Eventually what it's going to do is it's going to show me a URL in the bottom of this. It might be done. Might be able to do this. I don't know, let's find out. I think I gotta wait for this green dot to be here. Yep, here we go. Okay, so this is it. It's running my notebook on their site, because you can see this app, MyBinder, and this is the unique ID that's my Docker container, and this is the top level tree. So if I come into experiments, I look at modeling, I come down to Triode, and I run the iPython notebook. Okay, so now this one is running over at MyBinder. This is not the one I'm running on my local machine. It's the exact same notebook. Everything looks the same. And down at the bottom here's all the data. Here's the Python code to look at the data, the curve fitting algorithm. Here's K. And then here's the actual end result. So this last part here is really, really powerful because it lets me distribute notebooks and people can run my examples and play around with my analysis without having to set up anything. They can just do it right here. So what I ended up doing was I took this model and I said, all right, let's go back. And the triode's really pretty simple. The pentode's a little bit more complicated. I created the pentode model. Now the pentode model has an additional term in here called the this one here. There's a DG2 parameter that also needs to be extracted. So what this book here does, this Van der Veen book. Remember I told you about the SPICE model having his knee in it, and then this guy came along and Norman Corin came along and did some of his own model modifications to the original Leach model. So Minnow did some additional things to that, and what he ended up doing was he added in a term here to to simulate the grid, the screen current, and the interaction between the screen current and the anode current. And what he came up with an equation that he modeled themselves. So if you incorporate this alpha term in with K up here, you get this larger equation. And what Minnow ended up doing was he goes through and he calculates what N is and a couple of other things. So he uses this roundabout way, and he determines experimentally determines what all these parameters are, and he's able to curve fit that. So I did the exact same approach that I used on the triode model for the pentode, and I went in and I grabbed out this data here for a EL34, which is a pentode, power output pentode, and this one is coming in from Philips. Minnow is in the Netherlands, so we got to use the Philips data sheets. So here's the curves that are come out of that data sheet here. So I took those curves and I stuck them into, oh, I don't have a graph here. I'm missing something right here. Yeah, that's too bad. I'll have to go fix that. But I ended up taking the same data and I plotted that, and then I created the output curves. So this is the EL34 data sheet, the CSV file. Then I run that in to get the data in the right order. And then I run this curve fit algorithm from Python, SciPy's optimize routine. And I get out these values right here. Okay, so now I have 5 variables that I don't really know, but have a lot of experimental data. I run this through the curve fitting algorithm, and it determines the best match over all those data points with all those curves, and it determined these 5 values. So now I can take those values and use those in a SPICE simulation. All right, so here's the final output from all this rigmarole. Was these little tick marks are extracted data from the data sheets. These curves are the optimized, using a least squares optimization to figure out what those 5 parameters should be to make these curves as close to their counterpart tick marks as possible. So you can see I'm kind of not really matching up here, but I got a pretty good match along the way. Actually, this graph is kind of chunky over here, so I'm going to have to show you this thing running. Let me, I think we can come up here under cell and say run all. Let's see if this is going to work. It should work. There we go. Oh, it didn't work. Oh, great. Yeah, something's wrong. Now these values are wrong here. Let me get these values. Let me put some different values in here. The initial guess is really kind of critical on here we go. Okay, so here's my graph again. It's kind of chunky down here because I didn't put enough points in the curve. So over from the anode to cathode voltages, I'm doing 21 values from 0 to 400. Let's go ahead and make that 200. And I'm going to rerun it. So now my curves are really quite smooth. So this is running over there at MyBinder. It's running a Python interpreter, but it's actually displaying the results right here in my browser. So you can see how fast it was. It was really quite fast in doing those graphs. Okay, so this allows you to go and actually play with my my notebook, so to speak, and look at my analysis without having to install anything. This is the way that a lot of scientific community has adopted iPython notebooks for this very reason. People can download and they can run their own scenarios, validate all sorts of theoretical as well as experimental data without having to recreate the environment that the scientists used originally. All right, what's left over here. Well, we don't need to go into that. So with this, students that are taking Dr. Allen and my class can go in and determine these and do a little bit of analysis. So say that they want to pick, they have some tubes or they have access to tubes, or they want to design an amplifier. They want to actually do a design. Well, they need to know how to extract out these model parameters for actual devices in order to create the SPICE model to do their circuit simulation, to verify their design before they've actually built it. And in order to do that, you need a way to determine these parameters in the child-Langmuir equations. So that's where we are today. I published my GitHub repository. I'll have it in the notes down below. You're more than welcome to use MyBinder and point it to my GitHub repository and run these examples yourself. I think that's it for today. Thanks for watching. This is Valve Studio for March the 9th, 2016.